Log on, tune in, find out. Another good idea from Cambridge.
Little introduction.
Right, so just to start off, as Doug says, I come here from City University of New York, where we have a good logic group and where I have access to people who know a whole lot of different things. And so what I've tended to do is to look at other areas of mathematics, if possible, and go and ask irritating questions of a lot of other people about, in your area, can we do this? Hans Schoutens and Ken Kramer and Sascha Schlappentalk would all be among these people, definitely. Dennis Hirschfeld is more a computable model theorist like myself. So, yes, before we start, let me say there are certainly a number of open questions left over with this, some of which I'm working on with people right now, but some of which I'd love to work on with anybody who's interested. And I'll be here in Cambridge for another 9 days until through February the 1st, and then again for 2 weeks at the end of February, the 13th through the 27th, essentially. So if you're around, by all means come by. I'm in the office S4 upstairs, and always happy to talk about these things. Shall we try to go ahead with this? I mean, here's the first slide. See how it seems. People have been working on algorithms on fields for a long time. In fact, when the first computable model theorists crawled out of the primeval slime, they pretty much started thinking about algorithms on fields. It goes back a long time before this theorem, in fact. I mean, you know about processes for finding roots of polynomials and things like this that certainly go back to the Renaissance, and other algorithms that go back to the Greeks. I'm starting here because if you can read this, there is certainly some notion of modern computability theory here in a couple of different ways. So, first of all, Kronecker proved that there is an algorithm which decides reducibility of one variable polynomials over the rationals. So here's a rational polynomial. The way I've stated it here, it decides whether or not the polynomial has a root. Closely related question, does it factor at all over the rationals? Kronecker gave algorithms for deciding this. The first sense in which he was a computability theorist is that these algorithms were pretty much completely impractical. They would just take so long to execute that there wasn't a whole lot of point from an efficiency point of view. But as far as pure computability, is it computable? Yes, it is. He didn't use that word, but he gave an algorithm which we would consider a computable process. He then also considered the case of field extensions and proved that if the field extension is generated by a single element, and the ground field has what he calls a splitting algorithm here, then the extension field also does. And so the last two bullet points here, of course, cover all possible cases. The reason for separating them out like that is that the algorithms are different in the two different cases, extension by an algebraic element or by a transcendental. And one of the things which, of course, a computability theorist would tend to ask is, well, is there a single algorithm? First of all, if you're just given f of y, and you don't know whether y is algebraic or transcendental over f, is there a way to find out? And, well, failing that, maybe there's some way of putting these two algorithms together or coming up with a different one, which will give you the right answer in all cases, even if you don't know whether the y is algebraic or transcendental. So, as a matter of fact, the answer to both of those questions is no. You can't decide in general whether something is algebraic or transcendental. That would be a sigma 1 question, right? Being algebraic says there exists a polynomial over with coefficients in f, for which x is a root, and transcendental says there doesn't exist any such polynomial, and that's not decidable. And as a matter of fact, there also is no generalized splitting algorithm that covers the two cases. By all means, interrupt me with questions. Anybody, anytime. I hope that didn't need to be said, but just in case. Likewise, early 20th century, this is still before Turing, van der Waerden was trying to say, well, is this true for every field? Does every field, or at least every countable field, have a splitting algorithm? And he had some idea what he meant. He wanted to be able to do the field operations and to say, if we have that much, can we always come up with a splitting algorithm? And you can see reading him, he pretty much felt that the answer had to be no. But he couldn't say so because there was no formal definition of algorithm. You can't say there's no algorithm for doing it unless you know what you mean by an algorithm. And there just wasn't anything that really fit the bill up until, of course, the time of Turing. So, the rest of this story takes place post-Turing. And so we are now at the sort of Homo sapiens stage of computable model theory, where we can actually talk rigorously about this stuff. Let me go straight to the theorem here. So an awful lot of this comes out of the 1956 paper by Froelich and Shepardson, Explicit Procedures in Field Theory.
Which, by the way, uses exactly the same example out of Van der Waerden's book. Mm-hmm. Exactly, which then goes back to Emmy Notice Notes.
Mm-hmm. Okay. And so just Froelich and Shepardson proved a number of theorems which could not have happened before Turing, before we had a good definition of algorithm. Just an example to respond to what we had earlier, there certainly is, so they would have said, they said an explicitly presented field with no splitting algorithm. We would say a computable field. So a field where the elements are indexed by natural numbers and all of the field operations are computable as functions on the indices, binary functions. And so you can therefore give a computable presentation of the field here, the rational numbers extended by square roots of, well, the square root of the nth prime if and only if n is in the halting problem. Okay, halting problem is a computably enumerable set, and so it's not hard to present this field computably, exactly in the way I was just saying. But once you've done that, you see that, well, n is in the halting problem here, if and only if this particular polynomial has a root in this field. And so having a root clearly is not decidable. Likewise, factoring is not decidable by the exact same example. Okay, so starting with the Froelich and Shepardson paper, we really get into modern computable model theory here. I'm going to go back to Froelich and Shepardson, but let's stick with this topic for one more slide, and I'll tell you some of the things that have happened recently. So I've been conflating splitting algorithm, meaning does a polynomial factor, with the question of whether a polynomial has a root, and it's obvious that those are related, but one should formally separate them out from each other and write them out this way. Both of those, if the field is computable, both of those are naturally computably enumerable sets. And lots of times I give talks to general math departments and ask, which of those is a harder problem? Deciding whether p factors and deciding whether p has a root. And you get people arguing about this a bit. I think I'd say usually, if I ever put things to a vote, people would say determining whether it has a root is harder because it could factor without having a root, but not vice versa, at least for non-trivial cases. So that's a good way to get some conversation started in that context. In fact, Froelich and Shepardson showed that they showed that one is computable if and only if the other is, and really what they showed was that there are Turing reductions both ways. They didn't quite say it that way, but that's their proof. It relativizes perfectly easily. So those two sets are Turing equivalent, and in one direction the reduction is quite obvious. If you know which polynomials are reducible, you can certainly take a polynomial and reduce it into its irreducible factors and see if any of them is linear, and then you know if it has a root. The other direction is not so obvious. Froelich and Shepardson did give a proof which uses elementary symmetric polynomials. It's not the proof I would recommend reading, but it's there. It was the first one, as far as I know. There was a second proof in 1960, implicit at least in the paper of Michael Rabin, which we aren't going to focus on in this talk, but which is a very important paper in field theory. It deals with the algebraic closure of a computable field and how effectively that can be presented. And you can use Rabin's work to get a different reduction for the non-trivial direction, showing that SF is Turing reducible to RF. Okay. And then I stated just slightly more than I want. Oh, no, we're fine. The theorem that I'm giving here from just a couple years ago actually says in every computable field with a computable transcendence basis, the splitting set is 1 reducible to the root set. Okay, so algebraic fields, of course, the transcendence basis is the empty set. So no problem there. That covers this theorem. And so this is another Turing reduction from SF to RF, except it has this more specific property. I expect most of you remember what a 1 reduction is, but the idea is that if you're given a polynomial, P, coefficients in F, and you want to know whether it's in SF, you want to know whether it factors, there's a computable function which takes that polynomial, P, and outputs another one, Q, with the property that P factors over F if and only if Q has a root in F. Okay. And that's not incredibly hard, honestly. You can read the paper or talk to me, and I'll show you how we do it. It's not all that difficult. So that's a 1 reduction. It's stronger than being a Turing reduction. It's a special type of Turing reduction. And the interesting part of this was that in the same paper, I built a computable algebraic field where there's no 1 reduction in the other direction. Okay, so in some cases, of course, there is a 1 reduction, but not always, and in particular in the case of algebraic fields, not always. So the root set is, in some sense, definably harder to decide than the splitting set. It's a fairly fine gradation. They have the same Turing degree, but different 1 degrees. Okay, and so that gives an answer for me to finish off all those talks that I give to general math departments. In fact, this theorem has been trumped a bit by now. Rebecca Steiner is a student of mine at the CUNY Graduate Center, just finishing, and she strengthened the second result here by showing that you could even get the root set not to be bounded Turing reducible, or weak truth table reducible to the splitting set. So I think I'm going to assume that people either remember what that is or don't care right now what that is. I'm happy to talk about this later on. But the interesting thing about Rebecca's proof is that she determined exactly the conditions in which this reducibility fails, at least for algebraic fields, and it essentially comes down to the question of having, so if Q is the prime field, think of the rationals, it could also be Z mod P. If Q is the prime field, the question is, when you have two finite extensions of Q, one properly bigger than the other, is it, so if this is the case, then there are certainly polynomials which factor over K but not over L, polynomials with coefficients in L, let's say, which factor over K but not over L. However, all polynomials with coefficients in Q might actually go the same way. And so the bad situation in terms of this reduction, you fail to have this reduction if these two distinct fields factor or split exactly the same rational polynomials. Okay, and the question basically is, are there infinitely many such extensions within the field F? If so, then there is no BTT reduction, no bounded Turing reduction, and if not, then there is such a reduction. So good stuff there. But I want to move on to a different topic. I promised to come back to Froelich and Shepherdson here and tell you about other stuff that I work on. So this is not a modern theorem. This actually could have been proven more or less, at least by anybody back any time, at least since the beginning of Galois theory. It's based on the fact that if you're talking about normal algebraic extensions, then for a given irreducible polynomial over a ground field Q, all of the roots of Q in a field extension, in a normal field extension, are interchangeable with each other. There's an automorphism of the field extension mapping any of these roots to any other root that you want. So that being the case, Froelich and Shepardson were able to prove that for such a field, if you have two different computable presentations of that field, and so classically you know they're isomorphic, but the question was, is there always a computable isomorphism between them? In this situation, there always is. Essentially, given an element over here, you can find its minimal polynomial over the rationals, over Q, because Q has a splitting algorithm, Kronecker proved. And then you can say, okay, take the corresponding polynomial over here, the rationals map to the rationals in a unique way, which you can figure out. So take the corresponding polynomial over here and find one of its roots in this field. Now, there are several different roots, but they're all interchangeable. They're all in the same orbit under automorphisms of this field, so it doesn't matter which one you choose. You just take the first one you come to and map the root here to the root there. As you go along, you have to pay attention to the things you've already mapped, of course, and so you don't just take polynomials over Q, you take polynomials over Q extended by the finitely many elements that you've already mapped. But again, Kronecker said that you can do that, right? That's any finitely generated thing over Q. Everything here is algebraic, so there's no issue about that. And so Kronecker and standard procedures allow you to build an isomorphism. Okay. In modern terminology, we would have said that such fields are computably categorical. Froelich and Shepardson didn't call it that, but nevertheless, they had what, as far as I can tell, is absolutely the first example of a computably not categorical structure. The way they said it, there are two explicitly presented algebraic fields, we would say computable, and they said that those are isomorphic but not explicitly isomorphic. And that's exactly the negation of the definition of computably categorical, which is on the next slide. I can tell you very quickly the example here, which I believe is the one that Rod already had in mind. They actually proved this theorem twice, once in the algebraic case and once by playing games with transcendentals that become algebraic after a while. This is the algebraic case. The idea is to start with Q extended by all square roots of primes as both your field E and your field F, and then to build E and F up into bigger fields by adjoining certain square roots of square roots. So you want to make sure that there is no computable isomorphism, so you just lay out these two fields and wait for a potential computable isomorphism phi E to map the square root of 5 over here, let's say, to either of the square roots of 5 over here. And then you sort of tag the square roots of 5. You say, okay, over on this side, the square root of 5 that was mapped, I'm going to give it 2 square roots in this field. And of course, you can do that without giving square roots to the other square root of 5, right? Square roots of the positive one and not the negative one, think of it that way. Over on this side, if phi E mapped to this square root of 5, then you give 2 square roots to the other one. Whichever one it mapped to, you say, that was wrong. The two fields are still isomorphic, but phi E is not an isomorphism. And just by repeating this, using square roots of primes means that everything here is completely independent. You don't have to worry about a square root of 2 and a square root of 3 giving you a square root of 6 or anything silly like that. And so this is a very standard sort of construction these days, but it was the first of its kind to show that there is a computably not categorical structure. So the actual definition that we use is here. So it says that for every computable copy of the given structure A, copy of course means isomorphic structure but not necessarily computably. The definition says if the structure was just classically isomorphic, then in fact there really is a computable isomorphism. You don't have to go beyond the world of the computable to determine what's isomorphic and what isn't. And so this has been studied a good deal. And I don't intend to go into any of these examples. A lot more people than this have done more examples than this. But the usual goal with this sort of definition is to come up with an equivalent property for a particular theory, Boolean algebras, whatever it might be, to come up with a property equivalent to computable categoricity for computable models of that theory, but a property which ideally should be, well, a structural property, quote unquote. You have to be a little bit careful defining that. These are not first order properties as given. They talk about being, having finitely many of something or other. You could express at least the first three of these as L omega 1 omega formulas. For trees, the easiest way we know to state the property would take several slides all by itself. So it does get more complicated. But anyway, people do study this. There are several variations. I'll give you them all right here. Decomputable categoricity is probably best understood by an example. If you just take a very simple linear order, the natural numbers under less than, that's not computably categorical. Because if you give me a random computable copy of that, I can't tell what is the first element. And even if you let me make a lucky guess, I can't tell which is the second element or the third. That requires a one quantifier question to figure it out. So a zero prime oracle would be enough to compute isomorphisms between any two computable copies. And so zero prime, in some reasonable sense, is somehow ranks the difficulty of this linear order as far as looking at copies of it and matching them together. So zero prime can compute isomorphisms, but the zero itself, the degree of the empty set, cannot. And so we say that structure is zero prime computably categorical. Okay. All right. So the first conjecture was immediately exploded by Froelich and Shepardson themselves. Based on the previous slides, you probably would have said, well, finite transcendence degree. That seems like a good guess. Everything else had to do with finitely many adjacencies or finitely many atoms or something like this. Finite transcendence degree. Well, never mind. Froelich and typo there, Shepardson, of course, came up with an algebraic computable field which was not computably categorical. Okay. For algebraically closed fields, it turns out that the conjecture is true. And the other direction of the conjecture seems a lot more plausible. Infinite transcendence degree, it's generally hard, pi 1, to figure out if a number is transcendental or not. Transcendental says you do not satisfy any polynomial over the prime subfield. And so that question is no longer open, actually. And again, I'd love to talk about this outside when there's more time. But there is a computably categorical field of infinite transcendence degree over the rationals. And the idea there was sort of to take elements of the transcendence basis and tag them by making each one the first half of a pair which solves a particular polynomial. The polynomials that we used actually were Fermat polynomials, which makes it all sound very sexy because this was based on Fermat's theorem, therefore, in some way. It's pretty clear that you could do it with other polynomials as well. Fermat polynomials were the first ones which I, coming from outside of field theory, thought of. That's all. But anyway, so that's a nice example, which I'm not going to talk about anymore right now. For algebraic fields more generally, so algebraic fields are not too bad. I mean, you can sort of identify an element up to finitely many possibilities by figuring out its minimal polynomial. And again, the splitting algorithms for the ground field and things like this let you do that. So they're not especially bad. It turns out it's not too hard to show that they are all zero double prime computably categorical. They do not have to be zero prime computably categorical. There is a way, summarized here very briefly, of diagonalizing not just against computable isomorphisms, but against limits of computable functions, which might want to be isomorphisms. That has to do with the same sort of tagging process that I described before. The refinement is that remember before, we would tag 1 square root of 5 over here and the wrong one over in the other field. Okay, so you can start by doing that, but then later on, you could, if you wanted, you could add square roots of the second square root of 5 as well on both sides, and thereby untag, symmetrize everything all over again, and then use some other roots. It takes some moderately complicated polynomials. You can't just say, oh, use 7th roots or something like that, but some other roots to tag them the other way, so that even if this function here changes its mind back and forth as s increases, you can stay 1 step ahead of it at every step. If it ever converges, then you're 1 step ahead of it, and so it was wrong. And if it diverges, then of course this function is not an isomorphism, it's not even defined, and you do still have 2 isomorphic fields at the end of the day. So how hard is it? Well, 0 double prime, you try to code 0 double prime into isomorphisms in some way, into 2 fields, meaning that the fields should be isomorphic, but any isomorphism between them ought to compute 0 double prime, ought to compute maybe the set inf, something like that. That's hard. And it turns out it can't be done, in fact. So very quickly, the idea here is to think of isomorphisms as paths through a particular tree. If you've got these 2 fields, f and e, and so the x's here are the elements of f, and the y's are the element of e, you can say, okay, what could x0 map to? Well, I find its minimal polynomial, and I look for roots of that polynomial in y. And, I find one, and then later on I find another, and they're both potential images. Either of them might be a bad choice, of course. To think about what's a good choice and what's a bad choice, I can say, well, if x0 mapped here, what could x1 map to? Find the minimal polynomial of x1 over q of x0, and maybe eventually a root of that shows up. Maybe later on, yet another possible image of x0 shows up, and this tree is in general just enumerable. Well, in a sense, it's computable, but essentially you should think of it as an enumerable object. You cannot, in general, compute the branching of this tree. The way it's going here, it looks as though maybe y30 was the best choice for an image of x0, but you never know. Other stuff may show up as you keep on going. And so what you can say about this tree, although you can't get your hands on it perfectly, any path through it would be an embedding of f into e, and conversely, any embedding would be a path. And so you can talk about how difficult it is to say that 2 things are isomorphic. They're isomorphic if and only if there's embedding of each into the other. That's a special fact for algebraic fields, which would not be true for fields in general. And then the real point of all of this, skipping along, is to use the low basis theorem of Jakosh and Soar to say that for algebraic fields in general, there is a degree not below 0 prime, but low relative to 0 prime. So its jump is 0 double prime, such that every computable algebraic field is categorical in that degree. Okay, and essentially any PA degree relative to 0 prime works here. There are a number of interesting results having to do with that. There are fields for which there is no least degree in which the field is computably categorical. So where you can't really get your hands on the difficulty of isomorphisms the way you could with the linear order omega. Okay. Let's see, I think I'm going to run through this quickly and essentially just give you the theorems here. Work with Sasha Schlappentalk. We considered algebraic fields with splitting algorithms and got a fairly nice characterization of computable categoricity for them, which was, okay, so B sub f is the thing I skipped over on the previous page, so let me go back for just a second. B sub f is the relation of being in the same orbit under automorphisms. This is another pi02 relation. If you have a splitting algorithm, it's actually pi01, because the property of having a root then is decidable. So again, by all means, come and ask questions afterwards. I'm going to rush through this here. But with that, computability of the orbit relation is exactly equivalent to computable categoricity of the field itself, provided again that the field is algebraic with a splitting algorithm. And that turns out to be equivalent to relative computable categoricity as well. The complexity is sigma 3, as you can see pretty quickly. And the last set of theorems, which I was pretty sure I would just have to flash at you without actually going through them in any real detail, deal with fields where you, algebraic fields still, but where you don't necessarily have a splitting algorithm. So there is a characterization of relative computable categoricity for these. It's not very nice, right? It's not L omega 1 omega as far as I can tell. It talks about certain things being computable, just as in fact the characterization for fields with splitting algorithms did. The orbit relation had to be computable. So it's still open to say, is there some sort of reasonably nice, it's hard to formulate this question precisely, but some reasonably nice L omega 1 omega statement which is equivalent to relative computable categoricity here or in the previous theorem. If you're talking about just plain computable categoricity, we don't have a statement like that, but we do know how hard it is. It's pi04 complete. So the fact that it's pi04 definable comes from the fact that isomorphisms between being isomorphic for two such fields is a pi02 property, which actually was on a slide a while back, although went by pretty quickly. And so if you just take the definition of computable categoricity and plug that pi02 property in for being isomorphic, you get something that's pi04. And it does turn out to be pi04 complete. That's the hard part of this theorem, is coding a pi04, arbitrary pi04 set into the property. But yeah, that certainly shows then that it's not the same as relative computable categoricity, which is always sigma 03, and because one implies the other, there has to be a field which is computably categorical but not relatively so. And the very last theorem is completely separate. I haven't mentioned computable dimension at all, but the upshot of a separate part of that paper was that the interesting cases of finite computable dimension cannot happen for algebraic fields. So that comes mainly out of a theorem that Dennis Hirschfeld had in a previous paper, which refines the theorem of Goncharov. And I think at this point I will stop and leave it at that. There are some references here for computable fields, papers which have been very influential, going back to Froelich and Shepardson. And thanks very much.
Questions?
If you drop, on the previous slide, if you drop the assumption of algebraic, do you have an answer?
No. Sorry. Yeah, there. No, no, and no, respectively. So, I mean, the one answer we do have is that it's not the answer is not trivial. I mean, the conjecture would have been no field of infinite transcendence. Well, okay. One thing I can say, finite transcendence degree essentially behaves the same as algebraic. It requires knowing a transcendence basis, but that's only finitely much information. You have to be a little bit careful in positive characteristic because then you start to lose separability if you throw in transcendentals. And so that's not a place we've gone. But for finite transcendence degree, essentially the results still hold. In some cases, you lose some uniformity. You need to know finitely much stuff. But for infinite transcendence degree, I mean, we've only just figured out that the question is non-trivial, right? So, yeah, that's definitely still open.
Does that first theorem just follow from all that stuff about Scott families stuff?
Which theorem?
The relatively computable categorical by Goncharov's theorem, you know, it's open only if it has a RE Scott family, and is that the interpretation of the Scott family in the structure?
Once you get this condition, it's
A very strange
I mean, one direction is definitely, I have to remember which one now, it's been more than a year. One direction you essentially get by saying, okay, you know, having a Scott family gives you the, let's see, which way is it?
well, I mean,
If you
one of
know
the
this,
Goncharov's
then
theorems
it gives you a
was.
Scott family.
But Goncharov's theorem says the structure's relatively computable structure, relatively computable
If it has a signal.
has an
Scott
RE
family.
Scott family.
Right,
So
yeah.
then you just have to figure out what the Scott family says, infinitary
Yeah.
That's how omega 1 omega. I couldn't, anyway, we'll talk about it.
Yeah, I mean, it feels to me like a syntactical rather than a semantic thing. And again, I don't have a really good formulation of that question. Yes, okay, you can put it into L omega 1 omega, but you're talking about coming up with formulas, and I don't know how to express the question well. So, it's not as nice a formulation as, let's put it this way, saying finitely many adjacencies for a linear order just seems like a nicer thing than saying you have a sigma 1 Scott family. They're equivalent, but finitely many adjacencies is just something I can get across to a general math audience very quickly.
Oh, yeah. But
And I don't know how to.
you've got to talk to a
make
model
that
theorist.
Yeah.
All right, let's thank Russell again.